Hi everyone. In this video, which is our first video of the semester, we're going to start off with Chapter 2 of our book. Okay, Chapter 1 talks about statistics sort of things, and in our course, we're really going to, it's named Probability and Statistics for Engineers, and so we're really going to go over probability first, then statistics. And so we're starting off with the probability chapter, which is Chapter 2. So, here's a quick outline of the whole chapter. We'll only go through part of the chapter in this video, and so we'll work on in subsequent videos. But in our first video, we're going to cover sample spaces and events. Then we'll talk about properties of probability. We'll then talk about conditional probability, and we're going to end on the notion of probabilistic independence. Okay, and so we'll see what all that means in due time. So we're going to start with section 2.1, which is sample spaces and events. And these are sort of the building blocks in which we need to work up to what is probability. And it's going to seem probably weird for you to talk about this. It may not seem sort of normal because everyone has a notion of probability in their mind. If I told you what's the probability that something is going to happen, you can probably give it to me. And so you've come about this knowledge or come to this understanding of life, so on and so forth, through your many actions and experiences. But we've kind of have to leave those at the door and start from scratch here when we learn it more algorithmically. Okay, and so hopefully that makes sense, and you'll see maybe in a second. Okay, a lot of this stuff that we cover in this section is going to be very basic, but it is important because it does build up to what we know as probability. At least what we'll think about probability in this course. Okay, so we start off with the sample space. And so what is a sample space? The sample space of an experiment, which we denote by this script S, is the set of all possible outcomes of that experiment. And so I'm going to use the term experiment a lot in these videos and in class. It's any sort of random phenomena. Okay, and so that's what we're always interested in statistics and probability is a random phenomena. We're trying to understand that random phenomena. And so the first thing into understanding the random phenomena is trying to understand all the possible outcomes that can happen. We call that the sample space. So, for instance, my experiment could be flipping a coin twice. Okay, and thus the sample space of flipping a coin twice of my experiment are these four possibilities. Okay, so there's only four ways that flipping a coin twice can have an outcome, and the outcomes are heads, 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 tails, tails, heads, and tails, tails. Okay, so fairly simple, hopefully. Okay, that is a sample space. An event is any collection of outcomes contained in the sample space. Right? So it's sort of a subset of that sample space. It can contain one or more outcomes. So it doesn't have to just contain one outcome. It could be any subset of the sample space. So it may contain just one outcome. It may contain none outcomes. It may contain the whole sample space. Okay? So an event is quite wide-ranging. And so to go back to our example that I used before, flipping a coin twice, if I say the event A, so I'll usually use capital letters at the beginning of the alphabet to denote events. Okay, so the event A, if I let that be not the probability yet, but at least one head. Okay, so if we look at the sample space, which outcomes meet that condition? Well, two heads heads, 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 tails, and tails, heads. Okay, and so we see that event there has 3 possible outcomes. Okay, and I could let event B be both of them are tails, and so that again is a subset of the sample space, and it only has 1 outcome in it. Okay, so there are the sort of 2 kinds of events that you'll see. Okay, so your turn. Okay, so what are your turns? Well, they are examples that I put in these slides and in these videos throughout. There'll be probably at least one in each video. And what I want you to do with these your turns is to try them out yourself. In class, we'll use part of our time to go over these your turns. And so something like this is going to take just a few seconds, but there are other your turns that will be much more complicated. So here's our first one. Consider an experiment in which each of 3 vehicles taking a particular freeway exit either turn left or right. Okay, so they're coming off a highway. Okay, they take an exit, and at the end of the exit, you can either turn left or right. We're looking at 3 cars. And so I first want you to write out the sample space for the experiment, and then I want you to write out the outcomes for each of the 3 events A, B, and C. Okay, exactly 1 of the 3 vehicles turns right, at least 2 turn left, and all 3 cars turn in the same direction. Okay, so hopefully that is pretty clear what I'm asking for there, and we'll go over this your turn and others on Monday. Okay, and so let's move on here. After this your turn, you should pause and do this problem, but then after you're done, keep going to some sort of side effects or algebra that we can do with these spaces, or really what we should call them mathematically are sets. Okay, and so an event really is a set of outcomes. And so we can apply some elementary set theory to these events. Okay, so not everyone in here is probably familiar with set theory, but you've definitely encountered it in real life. And certainly if you're a computer scientist or a computer engineer, you know these sort of set theory algebras. So the first kind of set theoretic that we have is the complement of an event A. I'm going to denote the complement of an event A by A raised to the C power, and I'll always say A complement. Okay. Now the book, it denotes it as A with a apostrophe above the A. Okay. They're the same thing. I prefer the C. Other people prefer the apostrophe. But there is no difference. So if you're looking at the book and then looking at my notes and are confused, that's why. Same thing, different denotation. Okay. The complement of an event A is the set that contains all outcomes that are not in A. Okay, so if you're not in A, you're an A complement. Okay, and so this is like when you're younger and you have like rival gangs or friends, and you tell that friend either you're friends with me or you're friends with the other person. Okay, so if you're not with me, you are against me. So if you're not in A, you're in A complement. All right, so I don't know. That might have been a bad reference, but we'll keep on going. I'm full of them, and so you have to sort of deal with it. The union of 2 events, A and B, so now we're dealing with 2 events at once. Okay, the union of 2 events, A and B, are denoted by A, and then what looks like a U, but it's not quite a U, A union B. Okay, and so we read that in English as A or B. So the U looking thing, you'll always read as or. Okay, and if you want it sort of in mathematical notation, a lot of people call this like cup. So A cup B, A or B, consists of all outcomes that are either in A or in B or both. Okay, if you're in A or B, you might be in both. There's nothing saying that you can't be in both. Okay, so A or B. So that's the union. And the next logical step, if you're familiar with set theory, is the intersection. Okay, so we have the complement, the union, and the intersection. The intersection of two events A and B, denoted by A with this upside down U, a B, you read that in English, A and B, and in mathematical notation, they oftentimes call that like a cap. So A cap B consists of all outcomes that are in both A and B. Okay, so now you need to be in both. Okay, so that's the intersection. And so those are sort of the three basic set theoretic things that we can use to our advantage, or sort of that exist with these sets. And then if we use the intersection rule, or maybe a consequence of this intersection, is the notion of mutually exclusive or disjoint sets. Okay, and these are going to be important in the upcoming sections, especially when we get to independence. Okay, so for two events, A and B, when their intersection is the null set or the null events. So when A cap B is equal to the null set, which means there's nothing in it. So there are no events or no outcomes common to A and B. They are said to be mutually exclusive or disjoint. Okay, so mutually exclusive and disjoint are the same thing. Okay, so when two events are mutually exclusive, they have nothing in common. Nothing in common. So if you think of sort of mortal enemies, they have nothing in common. They are mutually exclusive or disjoint. Okay, and so that's going to be important for us. We'll talk about disjoint sets in just a second. Now, to visualize these types of things, we can use Venn diagrams. And so we will use Venn diagrams a lot to visualize these sets. And so our base Venn diagram here is in A. And so this to attribute this figure or graphic, this is straight from our book, the DeVore book. Figure A is our sort of base Venn diagram. And if you're unfamiliar with these, the box represents the sample space. So you'll notice in the bottom left corner of the box, there's that squiggly S, which we called the sample space. So the box represents the whole sample space. And then the circles represent each event. Okay, so A and B are two events. And so A is one circle, B is the other circle. Okay, and the base Venn diagram that we see, A and B do overlap some. Okay. If you look in B, now we have a shaded region, which is the crossover or the intersection of the two events A and B, and that shaded region represents A cap B, or the intersection of A and B. So one's common to both circles. For the union of A and B, that's part C, where all of both circles are shaded in. So if you're in A or B, you could be in A, just B, or the intersection. Okay, that all matches. Part D, and here's where you see the different notation for complement. Part D is showing you the complement. If you have a circle A and you have everything else in the box shaded in except for A. That's the complement of A. So if you're not in A, you're in A complement. Okay? And then the last part are mutually exclusive or disjoint events. And so that's when, in pictorially, Venn diagram style, A and B have no intersection. They don't cross at all. No events are common to both A and B. All right, so hopefully that makes sense. I believe you're probably familiar with Venn diagrams. And so I have your turn that's going to sort of test your ability to use Venn diagrams. Okay, and so what I want you to do is to use Venn diagrams to verify the following relationships for any event or any events A and B. Okay, and so you'll see the two events there. They read A or B complement is equal to A complement is equal to the intersection of A complement and B complement. And the second relationship is that A intersect B complement is equal to the union of A complement and B complement. Okay, that's how you would read them just in plain English. These two relationships are important, and so they're given special names, or they're at least honored by the person who sort of came up with it, usually, and that person here is De Morgan. And so these are called De Morgan's laws. And so basically what De Morgan's laws say is that when you carry that complement through, okay, so imagine doing some distributing here. If you go all the way back to your college algebra days, whenever you took algebra, you certainly did a lot of factoring and distributing. If you distribute that C through, it says that the set switches. So or changes to and. So that's the first relationship, A or B complement. Once the C's go through, the or switches to and, okay, and then it goes backwards. So what do I actually want you to do? I want you to draw a Venn diagram for each side of the equality and show that they are the same thing. Okay, so this might take some thought, and this your turn might take you some time, but do give it a try. Of course, we'll go over it in class on Monday. Okay, and so that's where we'll end this first video.